Hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Jeremy Gibbons, Professor of Computing at the University of Oxford, where I lead the Algebra Programming Research Group and teach on the Professional Master's Programme in Software Engineering. My research interests are in programming languages, especially functional programming and patterns in programming. You can find more on my background in the resources section of the console. For those of you who may be unfamiliar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on your screen. I think we can't actually see some of the highlights on the screen. So Jan, I've got Pedro's slides, not the ACM slides. But anyway, ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, and the ACM Turing Award and the ACM Prize in Computing, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. So before we get started, I'd like to mention a few housekeeping items. If you've got questions at any time, please type them in Zoom's Q&A button, not in the chat, in the separate Q&A widget. We'll organise the questions as Pedro speaks and try to get to as many as possible at the end of the talk. This session's been recorded and will be archived. You'll receive an email notification when it becomes available. And do check out learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it in to help us improve our tech talks. Today's presentation is by José Pedro Magalhães, and his title is Functional Programming in Financial Markets. Pedro is the managing director of leading a team of about 50 quantitative developers at Standard Chartered Bank. He's also one of the founders of Cordify, the chord recognition company website. Before joining Standard Chartered, he was a postdoc research assistant in the Department of Computer Science at Oxford, working with Ralph Hinzer and me on the Unifying Theories of Generic Programming project. Previously, Pedro was a PhD student at the Department of Information and Computing Sciences of Utrecht University in the Netherlands. His PhD thesis, Less is More, Generic Programming Theory and Practice, was about real-life data-type generic programming. So, Pedro, without further ado, please take it away.
Thank you very much, Jeremy. Hello, everyone. It's nice to see all the messages in the chat and where you all are from. That's not in my slides and it's not in my introduction either, so I'll just add that I'm speaking from London today. I'd also want to mention that this is joint work with my two colleagues from Standard Chartered, Atze Dijkstra and Pierre Neron, because this talk is based on a paper, an ICFP paper published last year, and they were the co-authors. But really, what we're doing here is reporting on the work of dozens of people over the years. In fact, before even either of us had joined the company. So it's a collective effort. I'm just here basically to tell the story about the work of many people and what's going on, what we do with functional programming at Standard Chartered. So I trust you can see my slides. I believe you have the option to view the different screens. So just go on. So here's a brief outline of what we're going to cover today. I'm first going to give you a bit of context, what financial markets are and how we do functional programming, or what functional programming is and what what are its typical uses in finance. Then I'm going to talk about Cortex and Mu. That's kind of the whole ecosystem of software we develop. Show you a few examples and then jump to conclusions and questions. So on context, and what are the financial markets? So financial markets is typically, it's a concept essentially. It's something that arises from individual contracts between large counterparties, financial institutions, banks, insurers, large corporates, etc. And inside financial markets, you typically have a function called quantitative analytics. That's because if you're a bank offering a suite of products, you have to have a way to differentiate yourself from the competition. You have to have a way to view, to make your own decisions on how you price your own financial products, how you, what aspects of market data do you consider important, more important or less important in terms of determining a price. And also you must have a way to see what you're exposed to in terms of market rates and fluctuations so that you can at all times be aware of your risk and how you can hedge it, for example. So this function exists essentially for that, to allow each player in financial markets to have their own view on their own book of trades. It is typically part of front office, and that's the case at Standard Chartered and also with my team. So that interaction with the sales and trading functions is more seamless, so that there are no organizational barriers to that. Priorities can change quickly, so it's a fast-paced environment. As markets change and as client demands change, so does the nature of the work we do. It's heavy on financial mathematics, and many things require a lot of compute power. You can think of Monte Carlo simulations, for example, are very common ways of pricing complex financial products. You simulate a lot of different states and then try to find potential expected paths in the large range of simulations. You have to take into account lots of conventions. One thing is to price something in theory. Something else is to do it in the real world, where you have to take into account business day conventions, like whether something is a holiday in a certain market or not. Or if you're dealing with commodities, you have to bear in mind that a barrel of oil is not really the same size in all the places that it's traded. All these things have to come together, and really you get quickly to the point where you have over 1 million data points to price a security. The way the teams are organized, so in quantitative analytics, you can essentially at Standard Chartered, we have the modeling and analytics group, which consists fundamentally of 2 subgroups. The core strats team, that's the team that I'm the head of. They are kind of the developers, quantitative develop specialists. We tend to not organize ourselves across business lines like foreign exchange, rates and credit, because the knowledge needed is typically more common across business lines than specialized. Quantitative analysis and quantitative finance, so the people that build the mathematical models, on the other hand, tend to be aligned to the business lines, because it's quite different. The modeling of products is quite different according to the different business lines. Now for functional programming, just a quick introduction, as it is not the most common programming paradigm out there. So most people are often used to imperative programming, where you have a sequence of imperative statements updating a shared immutable state. Whereas in functional programming, functions and function composition dominate. They are first-class citizens, so functions can return other functions and can take functions as arguments, for example. In my view, functional programming is particularly interesting if combined with purity. So not only are functions first class, but also you don't have unexpected side effects. Think, for example, if you have a function f with an argument x that returns a y, in a pure setting, you only need to evaluate that once. if second time around in the execution of a program you get an f of x, you know it's y. You need to evaluate it again because a file will not be deleted or created as a side effect, because with purity, there are no side effects. So that brings room to some optimizations. The roots functional programming are in lambda calculus. You can find out a lot about that. And some examples are Lisp, Scheme, Erlang, OCaml, Haskell, which is what we use at Standard Chartered, and F#. Now, for functional programming in finance, you can easily find, if you search online, the history of FP being used in places like Barclays and Standard Chartered, the banks, or James Street, which is a hedge fund, for at least 15 years. But let's not forget spreadsheets. And I came to learn and accept that spreadsheets are not only programs, but moreover, spreadsheets are functional programs. Now, whether you agree on that or not, spreadsheets were at the core of use of functional programming at Standard Chartered either way. So back in 2008, which is before I joined just around 10 years ago, there was some C++ code written by quants with modeling functions. So the raw piece that given a financial contract and market data provides a price or sensitivities. But trading and sales wanted to use that, but trading and sales don't use C++. They use Microsoft Excel and other tools. So a language was created as a form of a Microsoft Excel add-in called Lambda to bridge this gap. This allowed you to call the C++ code from Excel. But it already had a pure interface with supporting higher order functions and parametric polymorphism. It became quite popular. At some point, people started using it outside Excel, so just as a script. But at that point, it really also became clear that some better solution was needed. It had no module system, for example, so the scripts quickly grown out of hand. So in search of a full-fledged programming language, Haskell was considered as a candidate at that time, but we would lose the C++ and Excel interoperability that we already had, and also the ability to serialize all values, which was already possible back then and still is in Mu. So that's how Mu was created, as a dialect of Haskell, trying to stay very close to Haskell, but allowing us to preserve what we already had and mesh well with the existing ecosystem. Now, to describe in more detail Cortex. Cortex is essentially the entire ecosystem of what my team develops at Standard Chartered. My team and the wider team, so with the quants, the modeling and analytics group. I spoke about the Mu compiler and language. That's one part of Cortex, but Cortex also includes the C++, lots of C++ code, the Mu compiler itself, but also graphical user interfaces. So you see here a screenshot of a little app. This app is the home app, which essentially is just a launcher for other apps. This is all written in Mu. Not just graphical components, we also have server-side components that have no visual aspect to it. For example, an intraday risk service, and we also have several end-of-day batch-like analysis that can run through the entire live trade population. It also has interfaces so that it can be easily used from other environments. Excel is one example, but we also have interfaces to .NET, Java, and more recently Python. It is also built and tested and released automatically on a daily basis, and we're also responsible for this CI system because we have some specific needs, in particular with regards to how tests are run and how the code access is controlled. Who can change each part of the code. So here's a very concrete example of Mu. This is taken straight from our code base. And it's also code that runs in production on a daily basis. At first glance, I don't think you can tell this is Mu and not Haskell. and you very rarely can tell from syntax alone. And there are some very minor syntactic differences here and there in the languages, but not in this example. And yeah, most of the time you really cannot tell. So, but I assume lots of the audience here will not be familiar with Haskell, so I'm gonna guide you quickly through this code. This is a computation of some aggregate rate, essentially, given lists of transactions. So we're defining a function with this name that takes a list of transactions, FX transactions of some sort, another list of transactions, fixed income, and then returns a choice, may or may not return a choice. And then the way to read this, so as I said before, function composition is what we use typically in functional programming. And this works like mathematical function composition. So if you have f after g, that means g is applied first and f is applied second. So this is typically read from bottom to the top. So I see here that we take those fx swaps, we map a function over it. So for each fx swap, we get its amount and we multiply it by its rate of some sort. So, okay, some sort of scaling of the rate and the amount. And we sum all of those, we divide by an aggregate notional, and we add a spread. And then for the fixed income trades, we do basically the same, just with a slight difference here. Now we extract the notionals and rates from there because they have some different structure. And then finally, we return by looking at if any of the inputs is empty, then we take a 0 for that. And otherwise, we again do some sort of scaling of the rates, the notional via the rates divided by the aggregate notional. So I don't know your opinion, but in my opinion, this is quite readable. And it's the kind of code that if someone that is not a programmer but has some technical inclination and asks, how is the calculation of this particular aspect done in Cortex, I would just give them this piece of code and say, look, here it is. You can actually probably read it yourself. And I think, especially after you give a little brief explanation of how things can be read, a lot of code can be understood by people that have no programming experience. Now, there are some differences between Mu and Haskell, and I'll touch here on the biggest ones. Mu is a whole program compiler, so there's no separate compilation. This comes with some advantages, like that there are certain optimizations you can only do when you have the whole program in your hands as a compiler. But it comes also with disadvantages, the main one being increased compilation times. If you're working on an application that transitively imports 1 million lines of code and you change just one line, it doesn't matter if you change one line or 1 million, the recompilation time is the same because of the whole program nature of the compilation. It is an interpreted language at runtime, so the code is compiled to byte code, and then there's a small runtime interpreter. This means we can do things like compile code locally, so I can compile code on my Windows laptop and send it to run on a Linux server, because code generally is compatible. The runtime interpreter can generally interpret code produced by other Cortex versions and architecture. So this works across version and architecture. This is also very powerful when you want to do things like distributed computing. You can easily split the computation, run it on multiple nodes across the cloud, and then aggregate the results back. Haskell is a lazy language, meaning that the arguments to functions are evaluated on demand and not eagerly. Mu is mostly strict. I say mostly strict because this is not entirely straightforward. And it's also not entirely principled. The idea here was to do something that made sense, that made Mu not too different from Haskell, but still gave the benefits of strict evaluation, especially in terms of performance, as much as possible. So one particular example of where laziness is introduced in Mu is error handling, or a function like this. So if you have a from maybe, which is a function that takes a maybe value, which can be a just or a nothing, and if it's a just, it gives you the thing that is inside it. So in this case, you'd expect this to just return the singleton that is inside this value. If there was a nothing here, then we would get undefined, which is a runtime error. In a completely strict setting, this fails, because to evaluate from maybe, you evaluate the two arguments, and well, the first argument is undefined, so you fail. The same thing if you try to catch an error with a catch or try function. If you just immediately evaluate the argument, well, it fails, and you never get a chance to catch it. So lazy evaluation is introduced at certain key points in Mu, so that these things continue to work as people would expect. Strings in Haskell are lists of characters, not in Mu. They are native UTF-8 C++ strings. Calling C++ functions from Mu and vice versa is very easy. It's done natively without foreign function interface through a shared implementation of an ifunction interface. Recursion is, perhaps surprisingly for a functional programming language, discouraged and disabled by default in Mu. And this is connected to the previous point about C++. And the reason is that Mu has no tail call optimization. And it's actually quite hard to implement tail call optimization in this setting, because very easily you have a Mu function that calls a C++ function that calls a Mu function recursively, etc. So you have the interleaved stacks of each programming language in between. And you then can quickly run out of stack space. We found out that it is rarely needed. Under 4% of our modules actually enable recursion. And as a positive side effect, this leads people to use recursion combinators instead. So things like folds and maps, which have an efficient implementation, and which also make it more clear to see the pattern of recursion that is happening. There are some extensions we do not support, but serialization and deserialization is supported by default for almost everything in Mu. When we make great use of this to distribute code to be computed on the cloud. Now, I'm speaking about the differences, but actually we are trying to get closer to GHC. In the current compiler pipeline, it looks like this. So the compiler takes a Mu source, the front end produces exp, which is an internal representation, a small core language, and then optimizations are performed there, and the backend then generates bytecode. Now we want to replace this compiler front end with GHC directly, the main Haskell compiler, with the idea being that Mu would be taken by GHC. GHC would generate its own core language, and then a new piece of infrastructure, the GHC Mu compiler, will translate GHC core into the existing Mu exp language, and the rest of the pipeline stays unchanged, meaning we don't lose any of the benefits we already have in the backend, but we could simplify all the front end, like we wouldn't have to do parsing, for example. And hopefully this should also mean that adopting Haskell extensions will become easier, because at least all the front-end aspects of it will be covered by simply using GHC. We'd still, of course, have to care that we'd be able to translate that core into X, but still, many things should become easier or almost for free. Now, let me show you some examples of things we have in Cortex and built with Mu. For graphical, for graphical user interfaces, we use Widget, which is a library built on top of the Windows Presentation Foundation. And we essentially have different styles of using this widget library, but most recently we have built a virtual widget on top of the, let's call it, raw widget in model view controller, or perhaps more correctly, model view update style. And that helps keep the GUI and business logic separate. I think that's actually best seen with an example. was a little animation, but I'm afraid I was lost in the PDF version of these slides. So the idea here is that in this application, if you push the count button, it increments the number that it has there by 1. But you can also change the number to any number you want. And then if you push count, it continues incrementing from that number you entered. And here's how the implementation here's how this widget can be implemented in the 2 different styles. So this is the raw widget. As you see, it's very brief. Essentially, it's 4 lines of code. First, we define an int box initialized with 0. We define a button, which has a label count. And then we create an event handler on the actions of the button. And so if the button is clicked, we modify the input to apply the function suck, which is successor. So this is a +1 function. And then the result of this whole thing is the input horizontally next to the button. So yeah, very concise, but as you can see, we are mixing things here, right? The input is both this visual element, this text box, right? We're saying here that it goes next to the button, but it's also some sort of property that has a state, an integer state associated with it that we can modify. Whereas if you look on the right in the new virtual widget style, clearly more verbose, but we have a far clearer separation of concerns. We have to define what our state is, that's the model, and in this case, it's just an integer. And what messages the user interface supports. In this case, that's 2. Either we click on the button, and that's the only input, or we change the input to a given number. So those are the 2 operations supported. And now we have to say, given any of these possible messages, how do we update our model or state? Well, that's easy, right? If it's a click, we just use the successor function. Here's an example of how functions are first class in functional programming languages. So this update function takes 2 arguments and returns the result. Here you see only 1 argument. So on this side, we must have a function of type model to model, which is int to int. So indeed, successor is a function of type int to int. The other operation is to change the model to a given x. Well, then remember here we have to have a function. That function is the const x. That's the function that takes any argument. So it essentially ignores the current state and just replaces it with x. And then the view function, we define how these things look. So that's an int box horizontally next to a button with label count. And this is also where we tie things together. We say that on the change of this int box, we tag that with the message change, and on click of the button, we tag that with the message click. And then the main module pretty much just ties these functions together and initializes the app with the initial state of 0. So 2 different styles. Essentially, the more modern one is preferred for the advantages it has, and is also more functional, basically. I have another example here, but it doesn't have much, so I'll skip it. Now on to a more financial example. Quick Risk is the main pricing library, well, is the main gateway to all the pricing and risk sensitivity calculation functions in Cortex. It's essentially a one-stop API to access all of the analytics functions. From a functional perspective, one aspect that is interesting about it is how it dynamically generates type-driven workflows to determine what are the needed inputs from the desired outputs. So pricing a trade is not necessarily a simple thing. Here, you need different pieces of information, and you might also want to have different kinds of outputs. Here's an example, a typical example, or okay, the bottom we have a very simple example where with a given trade, all you need next to the trade is the market rates, and with that you can come up with a price. But you can also imagine a slightly more complicated scenario where the price alone doesn't tell you much. You may want to extend these trades with some common attributes so that it's more easy to interpret the results. Maybe you want to have the currency or the notional spelled out separately. And also remember, it might not be one trade, it might be 1,000 trades. So you want to have ways to distinguish between these. So in that case, you need a second attribute stage, which doesn't depend on the price or the market. It depends only on the trade, and it's combined together with the price to make up a result. So this second scenario is encoded by a single line quick risk call that looks like this. So you pass the input trade here, and you say that the result type you want to have from quick risk is a price stage. There's IO involved here. This is a side effecting function, so it's going to need to call a database to build a market, for example. That's what the IO stands for. But it's simply based on this, quick risk builds this computational graph that you see here at the bottom automatically for you. And if you ask for a result of type result, instead it will build this graph. So the computational graph itself is an abstract data type. And one thing is to build it, something else is to execute it. You can still then choose to evaluate this graph either sequentially or in parallel on your machine, out of process, or even on the cloud, so not locally. And there's also sharing of nodes during execution. One step further, if you start using quick risk a lot, and if you start using quick risk over large sets of trades to price, you find that you suddenly have a lot of jobs, and very quickly you have more jobs than you can run on your machine or on any given number of machines. So you find that you need a workflow management system. We have one, we built one, it's called Shepherd. It's all implemented in Mu as a robust process management strategy to deal well with operations that may crash. It itself is also quite resilient to the machine where it itself runs, if it restarts, for example. It can be used to define schedules, complex schedules, like to run something every day, every hour, every 5 minutes, or every specific hour on once a month or whatever. And it manages type dependencies between all sorts of different jobs. Jobs can run using multiple different Cortex versions, and it can be used as a library, client, or server. And here I have a screenshot of another GUI application in Cortex. This is the Shepherd client, which we use to monitor these workflows. And in this particular screenshot, you see a realistic quick risk workflow. So the previous one I showed was a simplified one. Here's a real one. So you see we still have trades as input. I assume you can see my mouse. Yeah. So you see the trades as input here on the left. Somewhere here, there's a market. Yes, here's a market node, you see. So that exists, but there's more things that need to be done before you're ready to build a market. The price is actually what we call the sanity stage. The result stage is here. But in this particular example, we're generating a data set as the final result. That's essentially an SQL-like database, which is a format that is very convenient to then ship away to any consumer because it's not Cortex specific in any way. And this screenshot shows the multiple states you may need to handle for a job. So the green ones have succeeded. They run successfully, all is good. The blue one, paths up here, is running, okay? Then we see a pink one here that is ready, but not running. So all its inputs are done. It could run, but it's not running. And in this case, I think it must be because it has no resources. So Shepherd has a concept of resources, and jobs have a concept of how many resources they need. Typically, you may have something like, I have 20 CPUs on my machine, and each job takes 1 CPU. So you may run out of CPUs, but CPU is an arbitrary thing. You can define anything you want as a resource. And Shepherd keeps track of resource availability, and jobs will be held if there are no resources. So the yellow ones are still waiting because their inputs haven't finished, but we also see some pink and red ones. So it looks like attribute internal here has failed, which means these two dependencies of it are blocked. They will never succeed because one of their inputs at least has failed. Still, that doesn't mean we need to discard or even stop evaluating the rest, because it could be that we just restart this failed node and it succeeds, and then we can reuse the whole thing and still produce a result. That's the kind of thing that Shepherd keeps track of and lets you do. All right, moving on to some conclusions. Sorry. Lots of numbers on this slide, so I could take a break to drink some water while you read some of them. So there's around 120 FTE, full-time equivalent, in the modeling and analytics group, and around half of that is my team, or strats. We have nearly 7.5 million lines of code in Mu, about 500,000 Haskell, and just under 2 million C++. 700 contributors over the past 15 years that the project has been live, and over 300,000 commits. Last year, as a representative example, we had over 7,000 pull requests. We have daily releases. Last year we had 302. Sometimes we miss a daily release for different reasons, but the goal is in general to have daily releases. On every code change, around 5,800 tests are run. This number keeps changing, but this should give you an idea, ballpark idea of how many tests. We have hundreds of applications, and the popular ones have more than 1,000 unique users each month. One representative large application consists of 850,000 lines of source code, so all the transitive dependencies, from around 4,000 modules. On the lines of code, I can show you the growth on a plot here. So the green on top is Mu. You see it starts at 0 at the beginning, because Mu was not there at the very beginning, so it was the C++ only time. Then you see Haskell, which is the dashed green. For example, the Mu compiler is written in Haskell, not Mu, so we do have a significant amount of Haskell code in the code base. So Haskell starts growing here, and then around 2013, 2014, Mu overtakes C++, that's the blue line, and you can see that the growth rates of the C++ code and Mu are quite different. As a side note, of course, we also have an app to load this kind of data and produce these kind of plots in Cortex itself. So that's a screenshot of that app here. So I'd like to conclude with some advantages of using functional programming in our setting. Entire classes of bugs are absent thanks to a strong static type system and memory management. And having pure functions by default and knowing where your effects are, and having basically or almost no explicit array indexing goes a long way in preventing bugs. It is the hardest bugs we have to deal with typically are C++ segmentation faults, and you simply don't have those in Mu. Well, unless it's Mu code that's calling C++ and C++ code seg faults, right? But I wouldn't call it a Mu code problem. We rely heavily on types of structure and even documentation if appropriate. Each different kind of financial product we trade, so for example, an FX forward or an interest rate swap, is modeled by a different data type in Mu. And we have dozens of these. So by the structure of a trade alone, you know what fields it has and what fields it does not have. You got a lot of structure given to you simply from the type system. On developer productivity, this is very hard to compare in a formal way, but I certainly believe that the use of functional programming allows us to deliver solutions faster or cheaper, which is kind of the same. Now, this is perhaps where you expect to see the disadvantages slide, but I don't actually think there are disadvantages of using functional programming. So I will instead address some common myths associated with functional programming. Some people say that it's hard to interoperate with systems built using functional programming. I don't think that's different in a setting without functional programming languages being involved. It's as soon as you start having large systems that are complex enough to require 2, 3, 4 different programming languages or tech stacks, you will have interoperability issues, and you just have to handle those like you normally handle. You can communicate by file, by database, or by building services, for example. None of that really is made any more difficult by use of functional languages. On performance, high-level programming languages are in general slower at runtime than low-level programming languages. That's not a myth, it's a fact. But I think there's often an exaggerated perception or concern for performance, runtime performance, in a deciding factor of how you do things. In our setting, we have both C++ and Mu readily available for solving most problems. And it's typically very clear what we need to use C++ for and what not. If you're implementing a tight numerical loop, some Monte Carlo simulation, or a data structure that's going to be heavily used and performance is going to be very important, then yes, C++ is the right choice there. You want to get the best performance you can. Other than that, you definitely want the safety that Mu brings you. And the performance impact is always negligible, as in if you have an application that starts by connecting to a database and fetching 1,000 trades, that alone will by far be much more than whatever penalty you may pay by using a high-level language rather than a low-level language. And you get all the benefits of having easier to debug code and fewer bugs to begin with. On hiring, yes, it's also often said that it's hard to find talent for programming in Haskell or functional languages. So I've hired over 100 developers. Whose main focus was to write Haskell and Mu, and it's never been a limiting factor in team growth, the lack of availability of candidates. In fact, sometimes it makes candidate selection easier. I've heard colleagues saying that for a Java role, they would get hundreds of CVs and they would have no way to go over these hundreds of CVs for a single role. Well, that's a problem I never had, but I've also never had the problem of not having a single CV or even not having a single good CV. And we required demonstrated functional programming experience for almost all our roles. And that's actually, yeah, that does narrow down the list of candidates, which simplifies the problem of finding good candidates. And we never really have a lack of good candidates. So in conclusion, functional programming has been really a catalyst in our setting, and I hope this little talk can help convince you to, if you need to be convinced, to try and use functional programming in other settings. There's a paper, so the slides have been or will be shared. There's a link to the paper that was published at ICFP last year in the slides. You can also just Google for that name if you want to read more about it. So thank you very much for your attention, and I'll take any questions now.
Thank you, Pedro. So, and thank you all for all the questions. I've been trying to collate them into some kind of order. So let's move on to them now. So I've picked some favorites. One of my favorite questions several people have asked, how come functions like fold are okay but not recursion? This is Julin asks, the speaker mentioned something about the former having efficient implementations. And somebody, Francisco Garau, says recursion is discouraged. Can you elaborate the example of how map is implemented or used in Mu?
Right, so essentially we have one primitive that has an efficient implementation, internal efficient implementation is specialized in the compiler. We implement things like map and fold in terms of that. We expose that function. Users can implement other functions using that as well. But general recursion, yeah, can do anything and can follow recursive styles that are not supported by that function, right? So it is that recursion that is discouraged and disabled by default.
So you have canned recursion patterns, and that's the thing that you encourage.
Right.
Good. That's the answer I wanted to hear.
Yeah.
There's a couple of Python-y questions. So Prakash Karambath asked, what are the distinct advantages of this kind of language over, say, Python, which may also offer some kind of functional programming?
All right, so the first disclaimer is I'm not a very experienced Python, or I'm not very knowledgeable about Python, but my experience with it is that Python is very flexible. You can do a lot of things in Python. And if you want, you can follow a very strict functional programming style, but you also can not follow a very strict functional programming style. So you can really do everything. Whereas with Haskell, you cannot. Well, at least not so easily, right? You could also just start doing everything in I/O, and then you're pretty much doing imperative programming. But I think the entire functional programming languages like Haskell and Mu are built to make functional programming in the strictest sense possible, easy, and the most the simplest way to do things in that language. Whereas languages like Python let you do things in many different styles, and also combine those styles, which can be something interesting and something that you cannot easily do in a functional programming language or in an imperative programming language, right? So yeah, I think that's what I would say is strictness on functionality.
Okay, so you take it as an advantage in being able to restrict the bad things people can do rather than enable some possibly good things and bad things with them.
Yes, and I guess that's actually a general pattern in things that I came to believe throughout my career, that taking away freedom from programmers is not necessarily a bad thing. And I still sometimes see people that aren't happy with Haskell because it's very hard to get the compiler to type check. I don't care if it has a type error. Why can't I just run it and see where the problem is? And yeah, I think that's the wrong mindset in the way. You have to pay a little extra time at the beginning to get your program right. But if you find out that if you do that, you may be spending far less time later on because you will not have bugs that have already been caught before.
Good. Yes. All right. Thank you. Benjamin Liss asks an AI question. Most AI-assisted coding tools use Python and other more widely adopted programming languages. I guess there's not such a large code base for Haskell, and certainly not for Mu to train these tools on. How do you think this will impact the future use of Mu and other functional programming languages?
Right, so that's a very good question. So let me take it in two parts. For most aspects, an AI model trained using Haskell is very useful for Mu programming. For most aspects, because the difference in the surface language is so small, and for the kind of programming we do, rarely there are things like laziness, for example, coming into play that would make a significant difference. Now, the fact that there's less code out there to train for Haskell than there is for Python, I don't know if that makes a practical difference. I don't know if there are studies on this. I'd be interested in reading, because that's definitely a fact, right? There are languages with much larger bodies of public code bases than others, and would be interesting to see if there's a correlation in how useful these models are. Although, of course, judging usefulness of AI models in coding is also itself a challenging task. Internally, though, we at Standard Chartered have our own teams working on AI, and we are looking into training or specializing a model with our own code base. So that is one way to address this. Another way is also to have clever prompts or pre-crafted prompts. You typically these days can give like a README to your LLM or to your coding assistant to say things like, this looks like Haskell, but isn't exactly Haskell. Here are some modules that we use very commonly that are not known elsewhere, but even just with a good prompt and some pointers to specific parts of the library that may be important, you can already get very good or much better behavior from an AI coding assistant. So to summarize, I'm not concerned. I think the general ideas of AI LLMs will transport over to Haskell and Mu. And again, Mu is getting closer and closer to Haskell, so I don't think that's a concern.
Okay, great, thank you. I have a couple of questions about why Mu. So why develop your own compiler for Mu instead of it being a DSL, I guess an embedded DSL, or just have it transpiled to a more popular functional language like Haskell or Elixir or Erlang? And somebody else says, why reinvent a lot of Haskell rather than just use GHC with the right combination of extensions?
Right, so I tried to cover that at the beginning. It's essentially historical. At the time this happened, maybe there was no foresight to predict that a full-fledged programming language would be needed. So something was built incrementally. First, something just to bridge the gap between C++ and Excel. And then at some point, there was already too much built into that was not supported by Haskell. Most notably, the ability to serialize everything. And the easy interoperability between C++ and also Excel. So yeah, that backend needed to be preserved, and it was not something that was readily available in Haskell, in GHC Haskell. And it's unclear if it would have been possible back then to just modify GHC to do that. Perhaps it would have not, I don't know. So I guess, yeah, in hindsight, and also we are trying to use more of GHC now, right? So in hindsight, maybe it would have been better to use Haskell directly and adapt it to our needs as much as possible. But that's just not what happened.
Okay, good, thank you. A couple of questions about open source. Philippe Vincent asks if Mu is open source, and Spencer Peloquin says, where can I find the documentation, source code, and binaries for Mu for use in a project? Is it embeddable in another language?
No, so Mu is not open source. It's a proprietary language. I actually forgot to mention that, sorry. It comes as, it's very obvious to me, but it's nowhere in my slides, sorry. Mu is proprietary. It's not available outside Standard Chartered, so no one can use it outside the company.
So let me ask, what would you say to somebody who says, this looks really cool, I wish I could do this kind of stuff, but I don't have a job at Standard Chartered?
I guess two answers. The easy one is we're often hiring, so maybe consider applying. No, but more seriously, I thought about that myself quite a lot. It would be great if we could open source parts of the Mu compiler. Now it's clear that we don't want and we cannot open source anything that has the financial models in it, or anywhere near that, like how we use market data, etc. But when you look at the exclusively technical bits of it, the language, the compiler, large parts, if not all, the UI library, and many of the applications, in particular, okay, not Quick Risk, but the other applications I've shown you. The problem is, this was never thought, there was never any thought to keep concerns separate from the start. And we're now in a code base that has around 10 million lines of combined C++, Mu, and Haskell, which we have to very carefully come through to ensure that we don't make any mistakes on what we can make public and we cannot make public. So it would be a very significant effort. I don't know if it's not an effort that it would be worth it, right? Because there are, of course, clear advantages to doing that. It would allow this whole ecosystem to grow outside the company. People could build their own things, fix bugs, whatever, and then Standard Chartered could also make use of that in return. So yeah, I'm not sure if it's worth it, but I'm sure that it is a very large effort. So that's why it hasn't happened really. And also because it wasn't thought from the start. Again, something that with hindsight, perhaps it should have been, right? But we don't always have the ability to plan things very careful from the start.
Okay, here's a question about the business case. The question from Ronald Munodawafa. How did you make the business case for functional programming against an imperative language, such as Python or Rust? How was it understood at the strategic level? And maybe the business case predated you at Standard Chartered, but how do you continue that business case?
Right. So yeah, the business case does predate me. Now we do have quite a lot of people that stay with the company for a long time. And my people leader is the one who created the original the Cortex project. And so in preparing this paper, I was speaking to people and asking how things came about. And that's one of the questions that comes up. My impression is that it was very organic, as in it was never a very clear decision. We're going to do this, is going to be the strategic new thing. This goes in line with kind of the answers I've been giving already. There was no big, careful, orchestrated thought for such a large thing from start. I think it grew very organically. There are some C++ libraries for pricing. Users are using Excel. How do we bridge this? Let's quickly build some language. We like functional style, so that language is in functional style. That also works nicely with Excel. And it kind of grew from there and it essentially snowballed. And at the point that we are now, it's very easy to continue to make the case because we are the only library for pricing all asset classes across financial markets at Standard Chartered. We are the strategic solution. There's nothing else. So kind of that the decision to accept this has been taken a long time ago. Was it hard? I don't know. I think, yeah, commonly there are these concerns about niche skills being required. But I guess you'll find that if you're looking at doing something really excellent and top performing, you need niche skills and top talent anywhere. So I think that wasn't too different, and we could show that we had something that worked. It grew over time, but it continued to work, be robust, and continued to deliver. So that was its own justification, really.
Okay, great. I have a pair of questions here about formal methods. Artem Lenski asked, do you use formal methods for proving the correctness of your Haskell or Mu functions or modules? And Gonzalez Huesca Lua del Carmen asks, do you incorporate some formal verification in your development? So some kind of quick check.
Okay. So, well, quick check, I would put more on the realm of testing. Right. So when I say we have 5,800 tests or so, some of those are unit tests, so typical input-output matches what you expect thing, but we also have quick checks, so property-based testing. They just need to be reproducible, so we run them with a fixed seed, but still that you can use that to cover a larger population than you would with the unit tests. We do not have formal verification. Yeah, I guess, yeah, that's just the answer. We don't have it. I think in my experience, I don't often see that in industry, unless we're talking about critical industries, often where lives are involved at stake. So aviation, for example, or medicine. But it's not something I came across in financial markets, not internally or otherwise. I guess you can see some research papers here and there, but it's not something commonly used in production.
Okay, great. Thank you, Pedro. I'm afraid that's all the time we have for questions today. The hour is nearly up. I'd like to thank Pedro again for his informative presentation and the insightful answers to the many questions. And a special thank you to each of you who's attended for taking the time to participate. This talk was recorded. I saw there were some questions about that in the chat. The recording will be available online shortly. at learning.acm.org. You can find announcements on upcoming talks and other ACM activities there and at acm.org. This is a reminder to please fill out the quick survey where you can suggest future topics or speakers, and you should see that on your screen in a moment. And if you have other recommendations as well, suggestions, I see there are several comments about participation certificates, so you might want to raise a comment about that. But anyway, let's end there. So on behalf of ACM and Pedro and myself, Jeremy, thank you again for coming. Thank you for joining us. I hope you'll join us again in the future. This concludes the talk.
Thank you, everyone.